Go, that is good. 5 seconds back.
Okay, welcome everybody. How's it going? How are things? All right. Thank you very much for your patience. The last week I've had a lot of stuff going on at home, so I'm very grateful for your patience. Hopefully though, the next couple weeks things stabilize a little bit. Are there any administrative questions about the class? How we're doing? Okay. We are giving back the exams at the end of class today. Prods should be coming in with them. The solutions are available, and there's a kind of an optional assignment. So if you have a case to be made on the grading of the exam, you're welcome to write out a page, or whatever, make a new cover page essentially, right, describing what the issue might be, and then include a scanned version of the entire exam and upload it before exam 2, and we'll review it. Okay. Any questions on that? Okay. Any questions about the technical content at this point? Bending stresses, more or less, hopefully under control. It's a very important thing to be able to do, to be able to figure out what the normal stress might be across a beam at a specific location. Okay? And the bending stress is what dominates the failure for beams that have, I guess you could say, some length, literally more than a scissors in many cases. And we'll talk about that today, in fact, because we're going to talk about shear. Okay, anything else? Or anything at all? Wow, we're quiet, folks. Okay, all right, well, here we go. So today, we're going to discuss shear. And in particular, we're going to do 3 cases. We're going to look at shear in kind of the scissor-like situation. Yeah, okay, yes. Oh, it's not on. Oh, that's a... Thank you. All right, we're going to look at shear in 3 situations. We're going to look at it in the case where you have essentially two plates on a pin, 3 plates on a pin, and then in beams. Okay, and so what do those look like? So the top one is what we're going to call single shear. So you see there's a pin going between 2 plates that have holes. And then this bottom case here, that's what we call double shear. All right. And then we're going to move to beams and look at what the internal shear force might be as a function of location. And you already know how to do that. And then we're going to relate that to the transverse shear stress. And the final thing we'll talk about, all right, and these are foreshadowing figures. Okay, you'll understand these things by the end of today. The final thing we'll talk about is the first moment of area. Okay, we've already discussed the second moment of area, where we have the integral of y squared dA. That's the second moment of area. So the first moment of area is where you have the integral of essentially y dA. Okay, so it looks something like this. Q is what we call the first moment of area. And so Q is going to be useful for calculating transverse shear stress, whereas the second moment of area, as you already know, the I, that's useful for calculating out the bending stresses. Okay? So with single shear, and we talked actually a little bit about this last time. You can imagine you have a beam. Okay, we're going to think of it as a beam, right? And the beam in this case is the vertical green member. And then you have two opposing blades, essentially, that come to try to cut this thing in half. All right, so there's a narrow gap, and we're going to assume that there's going to be this focused slice on which we have the shear stress. And so with this type of system, or with this configuration, we kind of talked about it last time, some kind of physical analogies, all right, will look like this pin. I'll go through that in a second. These kind of this pin or this bolt, okay, that has a couple of plates that could shear it, and we have also another type of pin configuration where you have two plates that are pulling a pin apart, or you could have as well scissors. Okay, we talked about that, or an ancient form of shears. I'm not quite sure what they did with these. Maybe they had their sheep. Okay, and of course industrial processes, or even just machine shop processes for shearing metal. Okay, but if we go back to what's happening with the physics, do you see that this green piece right here is the material that's on this gray in this gray region, and that is being sliced, and we have a force that is parallel to this surface, right? And so that, quite frankly, is going to be distributed, we're going to say, for our intents and purposes, more or less uniformly over that area, and that's going to be the shear stress. Okay? And you see that there is a shear stress on the bottom as well, and that is equal and opposite in its direction, and it has the same magnitude. Okay? So if I took the integral of all those shear stresses, dAs, like all the little ones, whatever that distribution is, right? And I said, minus the integral of all those shear stresses, dAs, right? That would be equal to 0. So this element, or this slice, better said, is under equilibrium. Straightforward? Okay, so that's single shear, and in some respects, I was thinking about this. Maybe we should have talked about single shear early on, because it gives you a pretty good physical example of what shear stress is. Okay, because we talked about shear stress in terms of an element, and it's causing it to tilt, and we have those shear stresses right on the four sides of the box. Okay, this is the practical way that you get a lot of shear. And as I mentioned last time we met, one of the reasons why we use shears is because materials fail. A lot of the ductile materials, okay, so the ones that, we've talked about ductile materials already, and we'll talk about them more, right? But the ones that don't just fracture when you go to the yield strength, right? These are the ones that will give you a little bit of and give you a little bit of modulus of toughness. Okay. Double shear is maybe a better way. So you can imagine if I need to secure two plates to each other, or if I have two plates with rivets, okay, like on a fuselage for an airplane, okay. This is one way to do it. Okay. Another way to do it is to have like a double plate, so a plate on top and a plate on bottom, and that is what we get when we talk about double shear. Okay. So in double shear, we have two narrow gaps instead of one. Okay? And so the shear stresses are spread between these two thin slices. So what does that mean? What does that mean? What's the magnitude of the shear stress going to be on these plates? Half, right? Okay, good. And so you get something, all right? If you want. Okay, sorry. So yeah, so it's half. Okay? And so if we look at it, right, we have this piece up here, this piece up here, and each of these is going to have half the force that we have from this piece coming into it. And once again, we can think of the shear stresses, okay, that are present on each of these thin slices in the material that we're slicing. Okay. And it looks, well, very similar, okay, to what I drew before. And the average shear stress is just going to be the force over twice the area. Okay. So if we're thinking about attempting to reduce the amount of shear, and so where is the shear, and when you see this and you see this, where is the shear really occurring? Which elements are experiencing the shear? Yes, I heard it, the bolt, right? That's what you were mouthing, right? The bolt is what experiences the shear, right? These plates, they're really going to be experiencing something more of like a normal stress, okay, in these regions. Okay. Now, there's also friction in between them. If this is clamped, you'll study bolt tightening in design of mechanical components, and so one of the things that you also are trying to do, okay, is to make it so that there is frictional contact between these two, so that would relieve some of the shear, okay, on the bolt itself. Okay, is that clear? Right. This is the bolt. This is what's experiencing the shear. Right. But if I have these plates that go around and they're clamped together with a normal loading, then these plates also are able to take some of that force in terms of a frictional contact. And when you look at bolt tightening and stuff, you'll see that there are these kind of rough approximations for the kind of the region that is experiencing this frictional contact, or the region that's under compression. Okay, even though the bolt head is maybe right here, and it only looks like it's going here, it actually causes there to be kind of this region that's all under compression that extends beyond. And this is a rough estimate. With finite element analysis, you can do a little bit better to figure out what that region looks like. But these problems are still nonetheless tricky, and there's a lot of, we can do the calculations, but there are going to be some factors and things that people keep in mind because of experience. So what are some other systems that take advantage of this double shear? Well, anyone bike? All right. Yeah, right. So this is a case, right, where you've got the fork, or even on the back end, right, on the frame, you've got kind of two supports that are going to be holding onto a shaft or some type of axle. Okay. Another example might be, anybody climb? Maybe climbers? No climbers. You climb? Okay, Brandon. All right. So yeah. So this is an example where you can see that you've got an opportunity to put a pin, okay, under two forces. Now, in this case, they're kind of far apart. All right. But in this kind of situation, you can see that it does make a closer approximation. Okay. So, single shear and double shear. So let's think about what shear would look like in the context of a beam. So we've talked about these pins, or these bars, that have kind of plates trying to essentially tear them apart, and they're not really, you don't really think of them as beams, okay? But we can think of them as beams. We can think of it in the context of, here is a beam, okay, and here is a force. Okay, so what are we talking about here? So let's say that this top piece was the fixed end of the beam, right? And now we've got this bottom piece, or vice versa, that's applying a transverse normal load. Can everybody see that? That's like rotated 90 degrees so that it looks like this. So we've already done this example a few times, okay, where we plot the shear force internally in the beam, and we plot the internal bending moment. And we can see that there's a maximum bending moment at this wall. Okay, and the bending moment is going to scale with the length. Okay, but the shear force, you see the shear force? Does it care about length? It does not care about length. Okay, so when are we going to see shear force having a larger impact on whether this structure fails? Well, if I make the beam longer and longer and longer, that means that minus PL, right, that gets larger and larger and larger. Okay? So, if I make it really long, PL has the opportunity, the bending moment has the opportunity to have a very large magnitude. And that means that PL, or the bending moment, that's what's going to dominate failure. But if I make L short, if I make L small, right, then there's a possibility that the bending moment is little itty bitty bitty bitty, okay? And when it's little itty bitty bitty, that means that the shear stress or the shear force is going to dominate. So this is for single shear. Similar story, okay, for double shear. Okay, now in this case, we'll say that I have a pin configuration or a pinned roller configuration. All right, so this is maybe pinned here, this is pinned here, and then I've got this force. Let's say that's the P right here. So once again, you see we rotate this diagram about 90 degrees to represent what we have here. And the pin configuration, we can think of these being the interfaces, or these are the thin slices, okay, over which you have a lot of shear. And if we draw the shear force, internal shear force diagram, it looks something like this. This is a good example, right, of when you have a concentrated force and we're going from left to right and it's acting downward, boom, it causes a big delta F or delta V. The delta V is equal to the P, or the minus P, right, in this case. That drops it down, all right? And you can go back and look at what we've been discussing in terms of diagramming shear force and bending moment diagrams, if you like. And the bending moment diagram looks something like this. It maxes out at PL over 4, okay, and it's going to be 0 and 0 at the pin and at the roller, right? And that makes sense because those boundary conditions, they're 0. Now this is, you could argue that these should be walls instead of pins, but that then actually brings us into an overconstrained problem, okay, an indeterminate problem. So that's a little harder to describe right here. We will get to those problems eventually, right? But this is a determinate problem where we can calculate out the internal bending moment and the internal shear force solely using equilibrium. Okay? We don't have to use constitutive relationships. Right? And you're thinking constitutive relationships, right? Yeah, we haven't described deflection yet of beams, and we're not going to do that for a long time, in fact. So, in this case, the average, okay, shear stress is going to be P over 2A. All right. So remember, this is P over 2, right? And that's the area, the cross section, right? So it's half of what you have for single shear. And once again, we see that if we make the L, right, if we make that beam very short in length, the maximum bending moment, right, is going to go to 0, right? If L is small, PL over 4 goes to 0. So that means, once again, if these, and like we were talking about that clevis for the mountain climbing, or the carabiner for the mountain climbing, or the clevis, right? Remember that one was they were pretty far apart. So that may not be the best example of double shear, okay? Because that double shear, that shear stress is going to be less, or internal shear force is probably going to be less than the bending moment, okay, that you have. And so once again, when the bending moment is, what's going on here? When the bending moment, right, is large, when we have lots of length, right, the bending stress is going to dominate failure. But for short beams, once again, the shear stress dominates. Any questions? Any thoughts on this? As a designer, hopefully, right, we were able to kind of look at these systems. Yes, you can do the detailed finite element analysis, which you will do, and in many cases now, because of the accessibility of these tools, you're going to have to do it for products that you might be designing. Okay? But before you even get to that point, you can kind of do some back of the envelope calculations or think in your head, oh, is this device going to fail because of shear? Is this device going to fail because of bending moments? Or is it going to fail because of a combination of things, right? Is it a rod that's going to be twisting that I'm going to have issues with shear? Is it going to be a bar? Is it going to be one of these pin configurations? So the first question that we have, and I can post a video on how to do this later so that we can get through material today, theoretical material, and concepts. But the idea here is just to show, when will the average shear stress be half the maximum bending moment? Okay, or maximum bending stress, sorry. Okay, so that's essentially saying, hey, I have an equation for shear stress, right? And I want that to be equal 1/2 the sigma bending, right? And I can figure out what the shear stress equations are, and I can figure out what the flexure formula tells me for the bending stress, right? And I can solve for what the length would have to be for this case to be held, okay? But I can go ahead and I can describe that in more detail. That will be a short problem. Okay. Another question will be for double shear and doing the same thing. Okay, so the other one, this one was doing for single shear, and the next question is for doing the same thing for double shear. Okay. All right, let's start talking more about what happens in a beam that has some length and how we're going to calculate this transverse shear stress. So now we have a pretty good way of calculating the shear stress if the length of the beam is very short, if these plates or these blades are very close to each other. But how do we calculate the transverse shear stress or the shear stress in a beam that is like the ones that we've been discussing? So let's think about a beam. Maybe it looks something like this. And we haven't described the equations for the deflection yet, but it's going to do something like that, right? You can imagine that we have, our handy-dandy eraser, and we're bending this thing with. Now in this case, okay, so in this configuration, I've got my roller, my pin, and I'm applying a force in the middle. Okay? And if I had this nice rubbery system, actually this probably will do, right? Except I'm probably not strong enough, or I don't have big enough hands. Okay, but you can kind of see it, right? It's bending. Did any of you, when you were in middle school, did you guys pencil fight? No? Okay, that might have been, yes? Okay, that was the thing in the 80s, no, 90s, and the thing in the 90s, and then the school said you were not allowed to do that, right? It's a waste of material, quite frankly, right? But you've got an idea of what it's like to bend a pen or pencil, okay? If we were to take apart this beam, or not take it apart, but think of it as a bunch of layers laminated to each other. And this is not a bad example, all right? Because you can find multiple situations where you might do this. If it's a composite material, if you're layering, you're layering up different fibrous epoxy mixtures, or even if you're layering pieces of wood. Okay, you have a wooden laminate. What is going to happen? What is going to happen with the relative motion of these pieces of laminates? Okay, these laminates. Well, you can kind of get an idea that things are going to slide a little bit, right? So it's going to look something like this, and okay, so it's going to slide kind of like this. This is my poor drawing, okay, of sliding. And with that sliding, what is that? What do you see? You see motion, right? You see relative motion between, say, this laminate and this laminate. In which direction? In the horizontal direction, or in the radius of curvature direction. Okay? So I've got sliding of surfaces internally. What does that look like? It looks like single shear, right? We just described this, right? Where you have essentially two surfaces. Now, granted, they are on a pin in the case of single shear, right? But you can get the idea that there's going to be some sliding. There's going to be some stresses between these laminates that are going to, and that those stresses are going to be along or parallel to the surfaces, and that's what we think of as shear stress. Okay, and in a little bit, you'll see that these shear stresses, okay, that you have present, they actually are maximum at the middle. Okay, or on the longitudinal or neutral axis. This is opposite of bending, right? In bending, opposite of bending stresses, right? Remember, bending stresses, sigma equals negative my over I, right? Y is the distance from the neutral axis, and y is equal to the thickness divided by 2, typically, right? Either at the top or the bottom. That's where the bending stresses are going to be the highest. These shear stresses are the exact opposite. Well, maybe not the exact opposite, but they are maximum at the neutral axis, but they are minimum at the outer surfaces. Okay, and we'll go through why that is the case. And yeah, I said last time that, cables are great because the bending stresses are 0 at the neutral axis, and you can leverage that quite a bit. In reality, yeah, you can have failure due to shear internally as well. Once again, though, as we'll see, as the length gets larger and larger for these beams, the shear stress becomes small compared to the bending stress. Okay? So in some respects, I can't say that how do you say this? We're doing a lot of mechanics exercises today because when it comes down to it, you're probably not going to care about transverse shear stress as much, okay? But it's actually quite a bit more effort to calculate them than it is to calculate the bending stresses, okay? And so you'll know that they exist. You'll know that if the beams are short, you have to think about this, but nonetheless, you're probably not going to use these equations as much, right? But the fundamental theory behind it expands our understanding of mechanics. Right? So here we go. Shear force along a beam. What does it look like? Well, once again, we've just got a force on one end, okay? And we can do the external equilibrium, and we do the internal for both, okay? And we can, this is just repeat, okay? Rinsing and, not rinsing, but repeating, okay? That's what the shear force looks like across the beam, right? We've already established this. Okay, so V. And if we think about taking a slice, right? So in this case, right, I'm saying, we've got let's not do it like that. We'll do, a slice, something like this. And this is a really bad drawing. Okay. And this is the, let's say this would be X, all right? And this is the shear force. Does this change? Let's see. Like that. Okay? That's internal shear force. You can begin to see that in some cases it's not going to be constant across the beam, but in this case it is constant across the beam. And this shear force, this internal shear force, is going to be distributed amongst this area, right? So once again, we can kind of see that if this has some area, right, the average is going to be just V over A. Okay? That's a force. It's parallel to the surface on which it's acting. Let's go into more detail here. So, I've lost my mouse. Okay, here we go. Okay. If we look at these DAs, right, like this, these little DAs, okay, we can say that there's these little shear stresses, and each one of these is going to be giving us a tiny amount of force, right? So dV, that's not volume, that is, right, a small bit of the transverse shear force. And so if I integrate this thing all up, right, I can write that V is going to be equal to the tau average over A, or times A, right? Right? Just the same thing with a little bit more detail than what I just drew here. Any questions on this? Right. Now, if we have a kind of a straight member, we can write that we have tau average is equal to V over A. We're going to assume that the shear stress is the same across the width, okay? And that doesn't mean it's the same across the height. Okay, we said that already. It's going to be higher at the neutral axis, and we'll get into that derivation in a little bit. Okay, but it is going to be, we're going to be assuming that it's the same across the width. And we're also going to do something kind of interesting in that we're going to take one of these elements, pop it out like this, and we're going to draw one of our shear stress that we've been calculating here on one face. Right? So now this element, what we're seeing here is just this. Okay, we're seeing this. See this? This is a face. We're seeing that face, which is this face right here. So that's a slice of the beam we've taken. And this element has to be in equilibrium. So if this element is in equilibrium, what other stresses do I have to draw on it? Yes? Okay, upward stress. Okay, that's true. Okay. So we do have to draw an upward stress. Where would that upward stress be? You're telling me I had to draw an upward stress. Okay. Okay. Well, does it have to be on the same face? This is a 3D element.
Can it be throughout the entire volume?
Okay. Right. So this is infinitesimally small, right? So you're right. Okay, there could be some type of normal stress on these faces. In reality, though, what we're thinking about is that it's going to be balanced by a normal stress on the backside, a normal shear stress on the backside, right? And to keep this thing from rotating, we had to have these other shear stresses, okay, that are acting, okay, on these other faces. Does this diagram look familiar? Now you see what I'm talking about? Okay, so yeah, so thank you for your contribution. All right, better aim that time. Okay, so the description, this type of ability to think about, okay, I can figure out the stress on one face, and that tells me what the stresses are on the other faces of this element, is very important. It's kind of similar to what we were talking about. Remember when we had the rods that we were twisting, where we said, hey, this is that cut on the rod. Let me just, what am I talking about? I'm talking about, remember when we had, oops, this type of situation, right? And we said there's a torque, and we're going to have these. If I look at the shear stresses, right? They're going to do something like this, and they go to 0, right? And then it's going to go the other direction, like that. Okay. This type of visualization is important because you start to look at elements. You start to look at, what if I have an element right here, right? What are the other shear stresses on the system that allow me to be in balance? Okay? And you can't just have one shear stress on one face of a material element, because then it won't be in equilibrium. Okay, so there have to be these stresses on kind of at least 4 sides of the cube, okay, for the element in the material. Is that clear? Any questions on that? Okay. And you see that these two, right, if I only had 2 of these stresses, like say this left one and this right one, that'd be causing it to rotate, in the clockwise direction. So now I have to have these 2 on the top and the bottom that would counteract that rotation. Yes, do you have a question? Okay, no, you're just thinking. All right, good. Okay, so now let's go ahead and begin the derivation for what the, calculated quantity of the shear stress will be, right? We've got nice, cute little images, and we were saying, hey, it's a tau, and yeah, if we know the V, right, we can figure out, and we know what the A is, then we can kind of figure out what the average shear stress would be. Okay. Notice again, before we even get to that quantitative calculation, the way I'm drawing these shear stresses. You see that these vectors are smaller, at the upper region and at the bottom region than they are on the kind of area right close to the neutral axis. And again, these transverse shear stresses are going to be 0 up here or down here on those outer surfaces, which is in contrast to the bending stresses, which are maximum at those upper and bottom areas. Okay, so what do? Well, let's go ahead and we'll take a slice, and with this slice, okay, it'll have a dx dimension, and we have a neutral axis, okay, and we're going to rotate this. If you can say, okay, if y is vertical, all right, and this is x, and then z is in the direction of the neutral axis, right? We're going to rotate essentially about y. Okay, so we rotate about y, and then we draw the following. Okay, what in the world are we looking at? Well, we're actually doing something kind of a little bit maybe ironic. We spent all this time talking about V, right? V. But now what we're doing is we're actually drawing the bending stresses. Okay? These bending stresses, now remember that dm dx is equal to V. Okay? So it's not like they're disconnected from each other completely, right? But for this derivation, we're going to start by looking at these bending stresses. And then we'll put a shear stress on this system as well, because we're going to slice in another direction in just a minute. Okay, but right now this is the bending stress profile, and this is a very thin element, right? And this dx, that of course is along the length of the beam. And we know how to calculate a bending stress, right? So the bending stress is going to be varying as a function of y, and as we said, it's going to be highest, right, as we get to the outskirts, right? As y becomes this like c distance, right? The distance from the neutral axis to the top, or like a minus c, the neutral axis to the bottom. And then once again, I is what we calculate for the entire cross section. Yeah, and we ask ourselves now, where is the shear stress? Well, we're going to take another slice. Okay. For this, we are going to. This is that rotated. This is this profile that you see here, and now I've cut away a bottom portion. Okay, that's what this dashedness is. So this is still dx in its width, like here. It's still dx, but the now we've got some region of interest that is a distance above the neutral axis. So what does this look like? Okay, so now we're going to define what we call y prime. And y prime, okay, is going to be above the neutral axis, and we have what we call an a prime. Okay. So A prime is the area. That's actually the area that we see here. Okay, so you can imagine that if you had some thickness and this neutral axis is halfway in between, then this would be something like the area A prime would be the thickness divided by 2, right? Because that'd be just between here and here, minus y prime times dx. And we'll get into those derivations, we'll get to that later, okay? We still had this bending moment on the left side, and we have this other bending moment on the right side, okay, m plus dm. So it changes, there's some small change in the bending moment. We had all our bending stresses, okay, and now we're just considering the ones that are acting on our selected region. This width is going to have on it the shear stress. Okay, so do you see that? How in the world? What just happened there? Where did this shear stress come from? Where did this shear stress come from? Anyone? Where did I pull that shear stress? Michael, I see you thinking. Did you have a thought? Any thoughts? Describe where that shear stress. How can I think of that shear stress? Or I can think of 2 interpretations of that shear stress. But what are you? And so what would be some? Where did that come from? Because that's kind of this is an interesting problem, right? Where did that shear stress come from? Or how do I define it? How do I explain its origins? What is the shear stress? Is this origin story? This is not Marvel Comics, right? Or whatever the DC. I don't even know what D stands for. All right, but what does D stand for? Huh? Detective? Oh, I had no idea. Okay. What? Okay, go ahead.
Because there's a rotation, so it's like around the point.
Okay, so there's a rotation. Yeah. Okay. We have to be. There has to be. There could be. Okay, kind of close-ish. Okay, other ideas? What do you think? Where did that shear stress come from? I see people gesturing, and if you're using your fingers, so I think there's some thought. Just speak up. Yes.
Is it because we have to maintain the equilibrium?
Okay, so when in doubt, say equilibrium in this class, right? So that's a good point, right? So that is actually one of the points that I wanted to. That's one of my origin stories. All right, here is that look, this sigma and this sigma prime, they're purposely drawn and they have different magnitudes, right? So right now, sigma prime, the way it's drawn, looks like it's a little bit bigger than sigma, right? And then of course it varies as height, right? So there's got to be something that plus this, right? That's going to compensate for this sigma prime, all right? So that's one aspect of it, okay? That's one origin story. Okay. Where else is this tau coming from? Other thoughts? Yes, Mark.
Difference in moments.
Okay, yeah, so we also have to balance moments, all right? That's true, okay, so that's true, yes?
It's because, like, since it's like attached, the thing we're looking at is attached to something, there'd be something pushing it this way, so it's going in the opposite direction.
Okay, yeah, okay, so let's go look, I think look at this. Remember what we said? There was a face, if we go back, remember this face was on this face, right? So this is an element, whoop, taken out of there, right? And we said there was a V coming downward, remember? And we said there was going to be some average shear stress on this face. There have to be 4 shear stresses. And look at this. This element, if this is this face rotated, there's a shear stress on the bottom. Okay? So, yeah, you could say, oh, there's going to be shear stresses on these sides as well. But for now, we're just interested in performing equilibrium in the horizontal direction. Okay? So this shear stress, you see, this shear stress is actually this shear stress. All right, so let's keep going. So now, all right, what we have is this shear stress and these bending stresses acting on a selected area, right? And this area, okay, is going to be this one. Okay. So we have some width, all right, and we have it acting a distance y prime. Oops, okay, so I'm sorry, I misspoke previously. See, I get confused too, especially during these tricky times. I'm sorry, this a prime is actually the width, not the dx width, but it's actually this t width. I'm sorry, it's this area. Okay, so this shear stress is actually acting on the bottom and it's coming out in the dx direction, and there are bending stresses, sigma and sigma prime, okay, that are involved here. Any questions on this? Any questions? Thoughts, comments, criticisms? Okay. So now let's go ahead and let's do the equilibrium. We're going to look at the balance of the normal stresses and shear stress acting on the bottom. Okay? This is the shear stress acting on the bottom. And when we do this, we'll say that we have shear stress times the thickness, or sorry, the width, which is t, not the thickness. The t is now the width, right? If we go back, see t is the width, right? Times dx, which is the very short length. We have the sigma dA prime, okay, so this is the sigma acting over this area, which we've described here. And we have a minus, right, the sigma prime over here acting against this whole thing. And this is going to be equal to 0. We have our equations for the bending stresses. So we have my over I here, and we have an m plus dm here. Okay? And Those we can knock out from each other. There, we can subtract them, and we get just that a dm is what dominates. And so now we can write that the shear stress is equal to dm, okay, over 1 t dx, and then there's an I, okay? And this is integral of y dA prime. Okay? Now, remember we had an important quantity integral of y squared dA, right? That's the second moment of area. And I made a very long video of describing that. Maybe some of you actually watched it. Maybe others of you are just like, this, get to the point, man. All right. This one, the y dA prime, is something that we will break down and look at as being called the first moment of area. It's not the second moment of area. Second moment of area with y squared. And then also the dm dx, right, is going to be equal to the shear, the transverse shear force. Okay. The way we call this first moment of area, the variable we give it, it's not I, which is what we had before, but it's Q. Okay. So it's now Q is equal to the integral of y dA prime over the region A prime. And the transverse shear stress formula is V quit. Okay, so don't quit on the transverse shear stress. Okay, VQ over IT. And this equation, we'll talk about how to go about solving problems with it, but it is significantly more difficult than what you have with bending stresses. But in reality, we're going to be, I'll show you some shortcuts that you can use for most cases. So then it becomes not that bad of a problem. So I think in most exams, I have not really asked people to do a detailed VQ over IT, okay, but they use some of these pre-derived expressions for maximum transverse shear stress. Any questions on this? Yes?
What does the little t represent?
The little t is representing the width. This is the width of the beam. Okay, so this piece is a chunk, right? If we're coming along the beam, right, and I take a slice, right? In this case, this is not a good example because my width is not constant, all right? Because I have a circular cross section. But if I had a rectangular cross section, so this is a rectangular cross section, it's the width of this cross section. Okay, good. All right, so we now have the shear formula. We have this new variable Q for the first moment of area. Okay, and we need to talk a little bit about how you can calculate Q in a practical sense. Okay, in a practical sense, so you don't have to run this interval every time. Right? We did that. Second moment of area for beam bending or for bending stresses. Right? You're not going to. I can't completely commit that you'll never use the integral of y squared dA directly on an exam, but you're probably going to use something like bh cubed over 12, right? Or pi over 4 c to the fourth, okay? Those would be the equations that you typically use because we're pretty much only using rectangular or some type of rectangular cross section or some type of circular cross section. And of course, we can hollow it out. So like the I-beam has a more complicated calculation of that, but again, I wouldn't recommend doing the integral. I would recommend just looking at an I-beam as a rectangular cross section minus a couple of rectangles. Okay, so let's talk about this version of Q, right? When we have area A prime, it has a centroid, right? Or every, okay, sorry, right? Any 2D shape, or actually any 3D shape, right? I can calculate a centroid for, right? And often under gravity, right, this is equivalent to the center of mass, right? So I can put my little finger there, I balance it, and everything's happy. And we're dealing with areas, so there's no density, there are no changes in density for these types of problems that we're going to be doing. And so, the center of mass and the center, or the centroid, or this first moment of area, okay, they're going to be essentially at the same location. And we'll talk about how to calculate those, all right? But you see this, if I have a centroid here, okay, which is where that point is, okay, and that I'm going to call y bar prime, that distance, okay? All I have to do is take the area, A prime, and multiply it by its height to that centroid, right? We're assuming that the centroid is halfway in between this side and this side, right? So when we talk about this y bar prime, we're just looking at the vertical distance from the centroid to the neutral axis. So this is kind of a shortcut for the first moment of area. Anyway, we can, we can write out that we have this this form of VQ over IT. It's an important one though, right? Look, what is V dependent on? V is dependent on where I am along the length. Okay? So, in the case where it's just a load on the end, right, we know that the internal shear force is just equal to this P, right? So V will have, well, it will be independent of X. But in general, you want to make sure you calculate your transverse shear force as a function of this X direction, right? And this, once again, highlights why we need to be able to draw shear force and bending moment diagrams, okay? Because we need, or at least why we need to be able to calculate the shear force as a function of location along the beam. The Q, all right, that is going to be dependent on what we call y prime. So that's dependent on where we are above the neutral axis. Okay? The I is only dependent on x. Okay, it's dependent on where we are, and it's the cross section. Right, that's the same as what we had for the bending stress calculations. And T, okay, this thickness, that is going to be dependent on where we are as a function of y prime, and actually it's also dependent on where we are as a function of x. Okay, but that is going to be this width. I don't really like this. Maybe we should change it, but the way the conventions that we're following here, when I think of like the I equals BH cubed over 12, right? That B is the width, all right? And often I'll think of like BT cubed over 12 or something like T would be a thickness, right? T in this case is the width thickness, all right? You got that? So when you see VQ over IT, this is not the thickness in the vertical direction. This is the effective B, the width, okay? So this is, we call it a thickness, but it's really more of a, I actually already did that. I highlighted it a few slides ago. It was the width, right? It's this width. Okay, let's keep going. So, there's going to be a problem that you get to look at where, and to see here's base B. So this base B is T, all right? And height H is going to be what I would consider to be the thickness. But what we say in this part of the course, we say that this is the height of the beam, okay, instead of the thickness of the beam. Thickness is the width. Go look at Hibbler. All right, that's just how it is. Okay. And so, what is the transverse shear stress at the neutral axis along the beam, where the internal shear force is V? All right, and what we're trying to say is, look, just Q is BH squared over 8. So you can do this problem with this hint. we haven't really talked about how to calculate Q, really, but you know how to calculate I. You know what T is, that's going to be the width, and you know what V is, all right? So you can calculate the shear stress, the transverse shear stress, right? This is just like, get a feel for the transverse shear stress, don't go bonkers. We're about to go bonkers. Okay. So what do we mean by bonkers? Well, we need to calculate Q, all right? So that previous question was, I told you what Q was, and that Q is what you have if you're at the neutral axis. But what is your Q, and we already kind of alluded to this, what is your Q if you are not at the neutral axis? Okay. Well, we said that it's going to be the first moment of area, and we said it's the centroid, or the distance to the centroid, times that area. So that distance to the centroid is the complicated part, at least in my opinion it is. Okay? And just to give an example of how you might think about this centroid, okay? Just imagine that you have some box with A prime as its area, and you have it with width or thickness now in terms of T and height H. Right? Where's the centroid? Well, the centroid can be calculated by this equation right here, okay? Or this equation right here, right? So if I know what the first moment of area is, I can say divide by A prime, and that will give me the location, the distance y bar prime to that centroid. Does that make sense? And then if I wanted to do this, if I wanted to find where it is in the horizontal direction, I could essentially do these into the same integral, not with respect to y, but with respect to x. Okay? But in this class, we really only care about the distance, the vertical distance of the centroid to the neutral axis. So A prime is equal to TH. All right, and what do we do again? Well, if we want to calculate dA prime, okay, we can think of it as the width times a slice, dy. You've kind of seen this before. We did this last time, okay, when we were looking at bending stresses. So now we can say that y bar, okay, of this system is going to be equal to the integral of 0 to h y t dy. That's the dA prime, or the dA, all right, divided by the area. And so we do this integral up top, and what's the area? The area is A prime is just the width times the height, right? That's TH. And so, as you already knew, the centroid is going to be here. It's halfway up on the height. Okay? So this is how you would go about calculating it with the integral. And this may be the last time, well, maybe not the last time. It's actually, yeah, I think it may not be the last time, but you're typically not going to have to do this type of integral. What you're going to do instead is look at where it is, y bar prime wise, and think about what the area of it is, and then calculate Q out that way. Okay? So if I were to balance this thing, okay, here's the point on which I would balance it, or this is the centroid, right? And this is halfway up H. If I were to do this integral, like we did here, with respect to x, then it would be half of t for the x coordinate, right? So similarly, right, x bar prime is equal to 1/2 t, and so we have that the centroid is going to be at 1/2 t, comma 1/2 h. Any questions? Yes.
Why do we have a part?
What's that?
Why do we have a part?
A symbol. Say that again. I'm sorry.
Why do we have a single part?
Simple one. Y prime. Oh, why do we have a prime? Okay. Yeah. Good. The prime is just the convention that we've introduced. This is really not, okay. You could have argued that we should have used the prime when we were looking at the location for calculating bending moment as well. right? But y by itself is typically just a y direction, right? So when we say my over I, or negative my over I for the bending stress, right? That is also a y, okay? The y prime allows us also to distinguish the difference between y prime and y bar prime, okay? The y prime, if we go back to it, the y prime is going to be the distance to the bottom. Okay, the y prime is the distance to the bottom of this area, and that is the location where we're interested in calculating the transverse shear stress. Right? So we're assuming it's the same across this length, and we're calculating it at y prime. Y bar prime is what we actually use to calculate out the transverse shear stress. Okay? Did that help at all?
So why do we have a
Why do we have a bar?
why?
Prime. We have the prime to help us distinguish. It's just a convention, all right? It's just a convention to help us understand that this is where we're calculating the transverse shear stress. Okay? You could just have written y here if you wanted, and written y bar if you wanted as well. Okay? But the convention, this is the convention that Hibbler uses. All right? Good question. Okay. So now, here's the shear formula again. This is the y bar prime is the distance to the centroid. Y prime is the distance to the location of the desired shear stress. All right. So these are the terminologies that we're using. All right. Let's look at calculating the shear stress on a rectangular cross section at a specific location. So now the location we want to calculate the transverse shear stress is not here at the centroid, right? That's the y bar prime. We want to calculate the transverse shear stress along this bottom length here that we're defining as y prime. Okay? And we're going to use the shear formula that we see here. And you see, like, I will sometimes not include the prime, all right? Or actually, how do you say this? This is actually maybe one reason why they include the prime. This integral is applied over the y coordinate, okay? You see, it's not y prime here. It's applied over the y coordinate over the a prime region. Okay. And then it ends up having a y bar prime distance here times the a prime. Okay. So let's look at this. To calculate the y bar prime, we need to know where this point is relative to the neutral axis, vertically. So to do this, you say, oh, I go up y prime to the location of interest, and I need to go halfway across the vertical direction of this rectangle. Okay? So what is that? Well, remember this total height is h, so the height from here to here is h over 2, and then if I subtract away the y prime, right, that gives me this length, right? H over 2 minus y prime gives me this length, and then if I need to go halfway, I divide that by 2, okay? And so now I have y prime plus the halfway length of the vertical direction to give me y bar prime. Everyone see that? That's boring. You'll fall asleep, but you're going to have fun doing this on problems, maybe, okay? So we can write out that the simplified form of this is going to be y prime over 2 plus h over 4. The a prime, okay, is going to be this width And we already calculated what the height of this was. That was the h over 2 minus y prime. Okay? And so that's the a prime. So therefore, if we look at q, q is going to be y bar prime times a prime, like this. All right? And now we figured out q. Q is the hardest thing to calculate for these problems, in my opinion. All right? I, you already have experience calculating. All right? I is going to be th cubed over 12, right? That's for the entire rectangular cross section. And so now the shear stress is going to be whatever V is. You know, you could argue that V is actually harder to calculate, I guess, because, you know, you have to have done the equilibrium across the beam to calculate what the shear force is. Okay? And then you have your Q, then you have your I, and then the T is just, again, that width at the bottom. And this can be simplified slightly and to be the following, and that will give us the response. So now you see this tau, the shear stress, is a function of y prime. So if you tell me, oh, you know, the beam has height of 1 meter, which would be a really large beam, right? But it has height of 1 meter, and you know, I want to be halfway up, you know, from the neutral axis, so that would be 0.25 meters, right? I could put 0.25 meters in for y prime, and then h would be 1 meter, and I can do this calculation. Nonetheless, we often care about maximums, right? You've seen that in the videos and various things. We care about what the maximum value is. So the maximum shear stress, we've already discussed this a little bit, is going to be at y prime equals 0. Okay. How is that so? How is that so? Well, one way to kind of think about that is, well, the only thing that depends on height is q, right? The I doesn't care about the only thing cares about the vertical location, right? Maybe not height. They all care. The others care about height, but the only thing cares about the y prime is the q, and that q is going to be maximum when you're at the neutral axis. You have the most area. Okay, your a prime is going to be the largest, right? Because the area will be essentially half the thickness, half the height, times the width, t. Okay. And so an equation that comes out often is the following. Okay? And this is one that you want to write on your formula sheet. Okay? Because I will probably ask on the next exam, what is the maximum transverse shear stress in this beam? Okay? And instead of doing all of this math, and if it's a rectangular cross section, which very likely it will be, all you have to do is figure out the average shear stress and multiply by 1.5. Okay? What is the average shear stress? Now people will get that confused. We'll forget. Well, the average shear stress is just whatever the calculated shear force is divided by the area of the cross section. Right? So, you know, when we had just the cantilever beam with a force on the end, transverse force on the end, you know, the V was constant across it. It's just P, right? So the average shear stress is going to be just P divided by the cross-sectional area of the beam. And now we're saying that the average, or the maximum shear stress, right? That's the average shear stress. So you have this idea that if that's the average shear stress, maybe it's not the maximum, right? Because we're saying it goes zero, it's 0 at the top and the bottom, but it's maximum at the middle location. Okay? So this is a classic expression. Another classic expression is, and I'm going to burn through this. You can do this if you like. But the other classic expression is for a circular beam, a cylindrical beam. It's not 3/2 times the average shear stress. It's 4/3. Okay. So if you get a rectangle, it's 3/2. If you get a circle, it's 4/3. And if all I ask is the maximum shear stress, you don't have to do all VQ. You don't have to do V quit. All right. You just calculate the shear stress, or you calculate the average shear stress, and then you multiply it by 4/3 if it's circular. Okay. If you have a thin-walled hollow cylinder, I probably won't ask you this, okay? Or if I did, I would tell you that the average, okay, times 2 is going to be the maximum shear stress. So that's like an angular, right? That's like, a ring essentially. So if you have a ring cross section, okay, that is the one that you can approximate, and that's for a thin-walled hollow cylinder. You can approximate it as twice the average shear stress. So that's a little bit more complicated because you had to figure out what the average area is, and so make sure you do the the outer diameter minus the inner diameters and the squares of those to figure out the area. The squares or the radii, whichever you're going to do to calculate that out. Okay. Hollow rectangular cross sections. I don't think I've put many of these on exams either. Okay, these are a little tricky. Okay, and figuring out where the maximum will be. All right, it will still be it'll still be at y prime equals 0. So it's still going to be at the neutral axis. All right, a couple ways to think about that are, well, Q will be largest there, but you have to do a Q over a couple of regions. You have to go from here to this location, and then from this location up to there, because the cross section has changed. Okay. So this is you can look at the slides, you can look at the math. We won't go through it right now, okay? But you can calculate the Q, and this is not super trivial, shall we say? Okay. And another way to think about Qs, all right, that is less about doing the calculus with the integral and more about essentially subtracting, right? We know we could add and subtract the second moment of areas especially when they had the centroid on the neutral axis, okay? Similarly, we can subtract and add Qs when we have a bottom surface, right, that is matched. So for example, on the neutral axis. So here what you're seeing is that if I have this cross section here, I can calculate the Q of the solid piece and then minus the Q of the region that's been cut out. All right, so, and there's another approach, if you so desire, where you look at it as cutting out these regions as well. Okay. We've talked a little bit about when max shear stress and max bending stress, which one dominates, and so we've already kind of done these equations, and now you can look at them from the perspective of saying the shear stress is maximum at the middle, and we can calculate out what it is based on, for example, if it's a rectangular cross section, 3/2 tau average. And there will be a problem like this, which I'll do. This is very similar to the last one, okay? And just a quick note there that I think it's much easier to go, since we're interested in something in this region, it's much easier to go from the right to the left I'll detail that again in a video that follows up, but we want to be able to look at the right end, which has no internal shear force and no internal bending moment at this right end, and it's because there's no constraint here, and that makes it much easier when we calculate what it is a distance from the right end when we calculate V and M. All right. Anyway, so what we did today was quite a bit. All right, we were able to talk about double shear, single shear, able to talk about how to relate shear force to transverse shear stress, and also discuss first moment of area. Any questions? Any thoughts? You guys want your attendance? Okay, give me 1 second here, because it is now time. Oh yeah, and we gotta pass. Let's start passing out the exams. All right. So, all right. Okay. All right.